Thank you to Console for inviting me. I'd like to take you now on a bit of a journey how we simulate our vacuum sensors, but I'm sure you don't really know what vacuum is because it's not so visible in everyday's life, or at least you don't appreciate it, I think. And it's not so well known as the automotive industry, even though Central Europe is a powerhouse in vacuum technology. So let me give you briefly an overview where vacuum technology is used and where you encounter it in your daily life. So here you see a list of products made using vacuum technology or uses vacuum in its operation. It basically started out with the lighting industry. The lighting industry was the driver of vacuum technology in its early days, starting with the incandescent light bulb you remember from your childhood, where there was vacuum inside the bulb to prevent the tungsten filament from burning out prematurely by the oxygen. But even today's modern lighting, they are manufactured using vacuum technology, be it the LED light emission diode or OLED and so on. Also, the display industry as a 2D lighting source uses, of course, vacuum technology in its production. But even if you go to the doctors and dentists, they may sterilize their tools using plasma sterilization technologies. Or if you have a broken bone and it's X-ray, the X-ray sources use vacuum technology. And if your blood sample is sent to the lab, there may be a liquid gas chromatograph or liquid chromatograph mass spectrometer to analyze the peptides and hormones in your blood to find out what's wrong with you. If you drink instant coffee, that has been freeze-dried with vacuum technology. If you have a house with solar panels, that is manufactured using vacuum technology, as all modern windows have thin film on top of it to reduce the emissive properties to bring the house into the energy regulations of these days. Or your glasses, if you have anti-glare filter on top of your glasses, that has been applied using thin film technology that is also using vacuum. Or if you have a cell phone, I'm sure most of you have a modern cell phone in your pocket, it would not work without vacuum technology. It contains a processor and many storage chips, and those are made using vacuum technology. Indeed, semiconductor industry is central to today's technological life, and in semiconductor industry, those chips, computer chips, processors, and storage chips are manufactured in an apparatus, something like this. It's a cluster tool coating machine. In the upper right, you see the wafer handler that brings in the wafer into the process chamber. The wafer is deposited on that wafer chuck. And above this open hole here is then a so-called shower head where the gas is introduced into the chamber to apply the thin films, coatings needed, or the etching gases to make the trenches. To manufacture modern CPUs takes quite some time, up to 6 months. We have noticed this in the Corona times, where it took a lengthy time to get the German automotive industry back on feet because chips are missing. So it takes about 6 months and hundreds of process steps to make such a wafer. If one of those process steps goes awry, you basically have to toss this wafer and it's discarded. So process control is really, really important in this industry. And that means sensors that give the signals to the process control have to be reliable and accurate at all times so that you get at a consistent quality at the end of your process. Now let me give you a few words about my company. Inficon is at the heart a sensor company. We make many different sensors using many different physical principles, different measurement technologies. So we have liquid and gas chromatograph, mass spectrometers. We have service tools for air conditioning technicians. We have leak detectors. We have total pressure gauges. We have quartz crystal monitors. We also have software, process control software for the semiconductor industry in particular. As a company, we are present in basically 4 different target markets. One is the semiconductor and vacuum coating. That's basically our largest market area. That includes semiconductor industry, but also solar panel manufacturing, optical coating industry, and display industry. Then there is the security and energy market. These are basically gas chromatograph, mass spectrometer portable ones for first responders, fire departments, or military personnel to detect if the gas out there is safe for you to breathe, or if it's toxic, or what kind of chemical is spilled out of the tank at a rail car accident, for example. Then we have the refrigeration, air conditioning, and automotive division or market area. That includes basically leak detectors to test, for example, the tubing at the rear of your refrigerator, if the tubing is leak tight, so that those coolant liquids do not evaporate into the atmosphere and contribute to the greenhouse gas warming. We also have then service tools for the air conditioning technician to maintain and service those air conditioners. And last but not least, we have the general vacuum market that includes R&D, but also dirtier industries like vacuum furnaces, steel remelting, but also industrial vacuum coating, and this can be coating for ladies' bags, knobs, for example. So as a company, we make many products, as I said, we're addressing different markets, and sometimes we customize it for important customers. As a company, we are present on the global market. We have factories in North America, Europe, and Asia. We have application and sales offices wherever there is semiconductor industry. In other countries, we have representatives. We are still a rather small company with 1,400 employees worldwide, but we are number 1 or 2 in our corresponding markets. The division where I come from is the Vacuum Control and Product division based in Balzers, Liechtenstein. We make total pressure sensors to determine the pressure inside the vacuum chamber, together with associated controllers and accessories to connect our products to the vacuum chamber. Now let me give you a brief journey how we grew with our simulation. It started out a little bit difficult. We had lengthy discussion with our management about the use of simulations. That simulations are more useful than pretty pictures. And after a while, we convinced the management, and we started out with a basic console license. But as we got better and simulated different aspects of our large product spectrum, we needed modules, so we added modules with time and as needed. And then we grew and we simulated more, so we have now an additional seat, and we actually do simulations for our sister companies. So we have evolved a bit into a center of competence for numerical simulation in our company. And in the future, I can see that we will build out our second seat, at least, with additional modules. And new employees come from the universities now already with a background of console simulation. So they want to do their own simulation. So we will need more licenses. And eventually our sister companies got the taste and need to get their own licenses to be closer to the R&D and turnaround. So let me give you a brief overview what kind of simulations we do, a wide spectrum, just a brief capture. Shown here is a mechanical simulation for a thin diaphragm that bends under pressure load and that is clamped in a mechanical structure. Using the console, we simulate this. We study the stresses caused by the clamping and by the inhomogeneities of the membrane. We want to make sure that this clamping is not affecting the lifetime, and we want to have the membrane operate as best as it can to improve sensitivity and the linearity of this sensing device. This sensing device is then built into our capacitance diaphragm gauge. Most of those products go into the semiconductor industry. We also do thermal simulations. Shown here is the simulation of a power printed circuit board where one of the components runs hot, and here we wanted to study the heat dissipation to the outside housing, because the outside housing cannot exceed 60 degrees centigrade. Otherwise, it's not safe to touch and you would burn your fingers. We always try to validate our simulations, and here we use the infrared camera to study it until we get confident that our simulations are up to the point. Recently, we also started to use optical sensors. We sell them now. Here we studied an optical emission spectroscopy gauge. It contains this cylindrical volume, and actually it's a plasma chamber. A plasma excites the molecules there, and there is a feeble light. And we want to make sure that we collect all the photons and focus it on the spectrometer with all the tolerances of alignment of the elements between the spectrometer and that plasma chamber. And so here we wanted to make sure that we have a high intensity signal and a sharp signal on the spectrometer, because we use this signal to analyze what kind of gas is inside the vacuum chamber. We also do AC/DC simulations. Shown here is the case of an inverted magnetron called cathode vacuum gauge. The issue here at hand is that we wanted to reduce the exterior magnetic field because there were new regulations coming in place in the semiconductor industry. The issue here is if you bring a strong magnet close to your breast, if that technician has a heart pacemaker, that strong magnetic field could basically reset his pacemaker and reprogram it. That's something you really don't want. So therefore, the exterior magnetic field has to be below a certain threshold, and we used console AC/DC simulations to help guide us for a new magnet design that fulfills this spec now. We also do simulations with hot ionization gauges using particle ray tracing module. The issue here is it operates basically like your old incandescent light bulb. You have a thin filament that is very hot, emits electrons. The electrons ionize the residual gas in the chamber. The created ions, you move away with the electrical fields to an ion collector, and the feeble current is then proportional to the vacuum pressure inside that volume. The problem here is Those hot filaments, 1,700 degrees centigrade, are rather thin structures held in place by a thicker mounting structure of a different material. So you have differences in coefficient of thermal expansion, and that leads to a warping of the filament, and the warping of the filament leads to a different sensitivity in the gauge. So that means you will have large uncertainty in the pressure measurement. And that's obviously undesirable in process industry as demanding as the semiconductor industry. So we wanted to move away from this delicate filament and create something which is more reproducible, more accurate, and transport stable. So to give you additional motivation, I show you here an example from a product we actually no longer sell, but it shows the issue quite clearly. To the left, you see 5 different sensors of the same type. They're compared with a reference, and you see that they deviate from the reference quite a bit, plus minus 30%. And that's no longer acceptable in the manufacturing industry. But even if you take the same turquoise gauge and make the same measurement over and over again, a repeat measurement, you see it varies still quite a bit, about 8%, and that's still too much these days. Also, the National Metrology Institutes, they wanted to have better sensors they can transport from one place to the other to make sure that their respective national standards agree very well and that those standards can promulgate it to industry. So they set up a European metrology program for industrial research and started a project that includes National Metrology Institute with the German PTB as the project coordinator. It included university and included national research labs or international research labs like CERN and 2 gauge manufacturers. And the goal was to create a gauge that is highly accurate, 1% highly repeatable, highly reproducible, very transportable, stable, that nothing happens when the gauge falls off the truck on the floor, and it should still behave the same as when it was calibrated for the first time. So within this project, we designed and optimized the new sensor completely on the computer. Only after we were satisfied with an optimal design, we built it. And that is the gauge we designed. The principle here is similar to the old ionization gauge, but here we replace the filament, the delicate filament that can easily warp, with a more sturdy disc filament that is much more robust to shocks and thermal expansion. And it emits electrons on a straight path through the ionization volume. And the electrons have to hit some place eventually, and this electron detector is hidden so that there are no unwanted secondaries that can influence the ionization and give us a high background signal. The created ions in the right-hand figure, the green ones, the ions are then guided away by electric potential to the rod, and that feeble ion current is again measured and is proportional to the vacuum pressure inside the chamber. The electrons, when they move through that space, they are actually focused using 2 different electron lenses. One is at the exit of the turquoise structure, the Wenelt cylinder. Then there is an additional focusing ring about a quarter of the length in here. They focus the electrons to the exit aperture so that they don't hit anything else in the yellowish ionization volume. While the electrons move through that volume, they have a little bit of an energy roller coaster, as you can see in the red curve. So they have a lower potential, higher kinetic energy. You have to take this in account when you do the simulation. The beauty of this design is that you can calculate the sensitivity of this gauge from first principles. All you need to know is the electron impact ionization cross-section for a particular gas and energy, and you can find that in the literature in your library. Also, it depends on the electron path length L that is given by the geometry and by the potential, and then the ion collection efficiency, which has been optimized to be close to 1, the temperature of the gas, and the Boltzmann constant. And because the electron impact ionization cross-section is dependent on the energy, you see on the right panel, that figure. So you have to take this into account when you do the calculation of the sensitivity. Okay, so we simulated everything on the computer using COMSOL. We built it, we tested it. 2 different manufacturers built a gauge independently, the different mechanical structures using the same electro-optical blueprint. And that's the outcome, basically. On the left side, you see 6 different units from manufacturer A, followed by 6 different units of manufacturer B, and they agree very well with each other. Of course, we also did COMSOL simulation, and that's the point to the right. And to our disappointment, it was a little bit low compared to the experiments. So we went back to our simulation and tried to figure out what was the issue. And turns out the issue was that we used a linear trajectory. We used basically the length of the black arrow in our simulation. If we would use the proper curved flight path of the electron, the red trajectory, then we arrive exactly at the experimental values. So we have great confidence that the simulation is to the point that we can trust our simulation, and we were very happy. COMSOL simulation also helped us in understanding experimental results. To the right, you see experiment changing the Reynolds voltage, and you see that there is a depression and a hump at particular voltages. We didn't understand this at first place, so went back to the COMSOL simulation and figured it out, that this must come from a non-nominal position of the cathode disk. If the cathode disk is moved a little bit to the side or is inclined a bit, we can exactly reproduce the dips and the humps at the exact Reynolds voltages. Maybe not exactly the amplitude, but obviously we didn't simulate the exact position of the disk here in this case. But still, we were very happy. I mean, here is the same thing once more. To the left is the optimal trajectory, and if you have different positions of the emitter, it causes different trajectories, and so we have to take care when we do the assembly of the gauge that we don't inadvertently move it somehow. And so we can test for it if the emitter disk is at its proper place. So I think we did a good job simulating this gauge, and the results are exceeding our expectations, exceeding the goals we set out to do. It has achieved the 1% accuracy, the 1% reproducibility, and it has been shipped around the world, and it agrees with the former calibration, so it's transport stable, so it has fulfilled all our goals. And that has been recognized recently as well. We got awarded the 2023 R&D 100 award. That's often touted as the Oscars of innovation, and awards it to the 100 best innovations that are up for sale within this year. We are very proud of that, and the product is now on sale with its associated controller, and we have on the graphical users interface on your computer, you see the COMSOL trajectory of the electrons, so COMSOL is always present when you use this gauge. And now I'd like to conclude. COMSOL simulations have now become an integral part of our product development. We use it regularly. We validate our simulations by experiments, at least as long as we have confidence. We get confidence into the simulations. COMSOL simulation was extremely helpful for us, especially in the learning phases of new modules. They were always helpful, guided us. It is really great to work with them. And as I said, in the near future, we'll build out the second seat with new licenses, add new modules. We continue to work with other divisions until they need their own capabilities. And I also like to say special thanks to Zoran Vidakovic and Sven Friedl and Fabio Greco of COMSOL Switzerland. They offered fantastic support to us. They were always ready to help us. And the few times they couldn't really help us, the COMSOL development team in Massachusetts was ready to help us and guided us. And on a few cases, they even made modifications in the next release to help us better. I also like to thank Francesco Scuderi, who is here in the audience and had a poster yesterday. And he had many of the simulations done I showed you in this talk, but also my other colleagues at Inficon helped. I thank for fruitful discussion, and of course I'd like to thank the MP project, without which we wouldn't have started this development of that new gauge. Thank you very much.